The term physics is derived from the study of nature. As the natural science that studies physical matter, it's quite disconcerting to see its portrayal in the virtual world.
In this clip, the bus is approaching a bridge that is completely absent, and the driver revs up the motor and goes fast enough to miraculously overcome that gap. There's no incline on the bridge, and the platform it lands on is at the exact same level.
Under this house, I actually have a lot of watermelons in this house. Yeah. Ironically, we're having a food crisis.
For example, the kinematics behind firearms are actually quite interesting. Shooting any type of gun involves physics ranging from friction, force, momentum, kinetic energy, transfer of energy, gravity, heat, sound, and projectile motion in order to hit its target. Although we usually see mechanical energy turning into heat or thermal energy due to friction, in a gun the opposite actually happens. Thermal energy turns into mechanical energy. How does this happen? Well, first, when you press the trigger, a part called the hammer strikes the back of the bullet, and the gunpowder inside explodes. This causes a lot of heat to be generated, and hot air expands, so the gases in the gun expand to propel the bullet outwards. So if we were to draw buckets, it would look something like this. So we're going to start this from the perspective of the bullet. Now the bullet has a bunch of gunpowder in it, which we can consider as potential energy. There is no kinetic energy because the bullet's not yet moving, and there's no thermal energy either because we haven't triggered the explosion yet. When you take the hammer and strike the back of the bullet, it triggers the explosion. And what happens here is that our potential energy turns into thermal energy. Now, note that not all of the potential energy turns into thermal energy because not all of the gunpowder usually explodes successfully, but most of it does. So we'll just say that all of the U turns into thermal energy. Now, this thermal energy is important because it makes the gases hot, which causes a very interesting transfer of energy from thermal energy to kinetic energy. So this goes into here. Basically, that huge expansion of gas causes the bullet to go forwards a lot, which results in a high velocity, and that's what causes kinetic energy to result. But we have to keep in mind that since heat is not really easy to work with, a lot of it is lost into stuff like light, which you can see when you fire any gun. There's usually muzzle flash. You might also know about the bang sound a gun makes that is caused by the vibrations caused by the gas explosion you hear as sound energy escaping from the gun. In automatic weapons, the thermal energy in the form of expanded gas is used very cleverly. It forces a mechanism back into kinetic energy in order to compress a spring while ejecting the spent bullet shell. The spring's potential energy then turns back into kinetic energy as it forces the mechanism back, and in doing so, the mechanism loads another bullet to be fired. This is why it's called automatic, because we're lazy and we don't want to do all the stuff ourselves. Recoil is often simulated in shooter games as a random calculation of how far your bullets will land when compared to the crosshair on screen. For example, this game uses a physical pattern combined with mathematical uncertainty to determine where the bullet will ultimately land. By faking it, games fail to calculate many of the physical aspects that should be taken into account in this situation. These include gravity, drag, and wind force, which all affect the acceleration of the bullet in different ways. However, in this video, we're going to be talking about how the mechanics behind the gun's kickback or recoil works when a bullet is fired. Alright, so let's consider Newton's third law. Every action has an equal and an opposite reaction. So in other words, momentum is conserved. So momentum is conserved. Okay, let's consider a situation where we've got a 60 kilogram man, or I should say man-gun system, because including the gun, he is 60 kilograms, right? Okay, this shooter has no pants on. He is firing 240 grain, or in other words, a 0.016 kilogram bullet, and going at 360 meters per second when it leaves the gun. We know that the bullet is moving forwards because it's moving at 360 meters per second, but if conservation of momentum is true, then this man is in all actuality also moving backwards some amount that we do not know, velocity of the shooter. If we do a short calculation, we can kind of figure out how fast the shooter is moving backwards. But first, let's make it so that this guy is standing, or the shooter is standing on a frictionless surface, so we don't have to worry about friction and all that stuff when we're considering this. So first, we start with our PF equals PI equation, conservation of momentum. So we can consider this kind of situation as a collision. It may not look like a collision, but it really resembles one, doesn't it? Because the man and the bullet are moving the opposite direction, just like as if they were hitting each other or colliding with each other. So in this collision, we're gonna have to, so the final momentum after the collision is equal to the momentum of the shooter plus the momentum of the bullet, right? And that is equal to the initial momentum, which before the firing or anything actually happens is 0. So PS plus PB equals 0. Now let's move PB to the other side. So we can see that the momentum of the shooter is equal to negative the momentum of the bullet, because they're moving in opposite directions, as you can see here. So let's plug in mass and velocity. So the mass of the shooter times the velocity of the shooter is equal to negative the mass of the bullet times the velocity of the bullet, right? So to get velocity of the shooter, that's what we're trying to solve for here, remember? Because we don't know what the velocity of the shooter is. We know what every other thing is, but except for the velocity of the shooter, we're going to solve for velocity of the shooter. So the way we do that is we just, very simple, divide both sides by the mass of the shooter. Okay? So let's actually do this using the real values here. Something like 0.096 meters per second. So we can see that the shooter, although he isn't moving very much, he is moving due to the conservation of momentum principle. Now, in real life, when you shoot a gun, you don't just slide in one direction backwards. First of all, that's because there's friction here. So we didn't take that into account. But also another reason is that the man is a system. The gun, including the gun, it's a shooter gun system. So the gun really only touches his arm and maybe his chest. So that's what absorbs most of the momentum and goes backwards. Alright? So that's what these games are kind of trying to simulate, is this velocity that occurs when the gun hits your arms and your chest. Okay, so we now have the velocity of the shooter, but let's take this momentum is conserved idea to another level. Interestingly enough, if this guy was shooting at someone, which he really shouldn't be, but let's say he was, right, there's now a target who's being shot. Okay, this target, alright, the momentum is still conserved in the bullet. The same momentum acts upon him. But why is it that he has the side effect, or the target has the side effect of being shot, while the shooter only feels recoil or kickback? There's a reason for this that we can demonstrate using another calculation. What's different is actually the kinetic energy. Alright? The kinetic energy of the shooter after he shoots the gun is equal to half the mass of the shooter times the velocity of the shooter squared, right? And if you do this, 0.55296 joules. When we take the kinetic energy of the bullet, okay, so KB equals half m of the bullet, right? Mass of the bullet times velocity of bullet squared. So it is 360, and we come up with 2,073 joules, right? This is huge, alright? This is huge, okay? Compare these two numbers, alright? This, alright, is barely anything compared to the huge amount of energy that is in the bullet, okay? So this kinetic energy that's in the bullet, okay? Let me draw a bucket here. This huge amount of kinetic energy in the bullet is what is transferred all the way into this guy, okay? And as you know, when a lot of kinetic energy goes into your body, there's a side effect of maybe feeling a lot of pain. While this guy here, okay, he barely feels anything, okay? He feels like this much kinetic energy. So that's just a little bit of velocity here. But to this guy, he's absorbing 2,073 joules compared to this guy's 0.55296 joules, alright? Which is crazy, okay? That's why guns are dangerous. Even though the momentum felt by the shooter and the target is the same, okay? The huge discrepancy in kinetic energy is what makes a bullet dangerous, despite Newton's third law. In short, because they don't portray it correctly, it's impossible to explain physical concepts through video games, movies, or any other type of entertainment media, despite our best efforts.
And this is our physics for everyone, and by everyone we mean league players, because league players are the only real people, and by
momentum, represented as P, is equal to the mass times velocity. As you can see here, Alistar, the blue cow, headbutts Sona, the floating woman. Momentum is conserved in any collision.
To understand how something works, you actually need to look at the real physical concepts behind it.